Now let's move on to a simulation in civil engineering systems, which is another powerful tool that builds, on probability and on modeling to help us design somehow a fake, or not a fake, like a parallel universe, right, to reality so that we can do stuff and predict stuff and have a small little project that is a replica of the actual one, but for, if not for free, for way less money. And this is chapter 8 from the book that we have been using by Dr. Labi. So civil systems are inherently complex and uncertain. Like nothing, you can't replicate anything 100% each and every time. So how do we deal with unpredictable loads, unpredictable traffic patterns, unpredictable weather conditions, and unpredictable finances and funding? We use simulation. Simulation is a tool that helps us test and optimize ideas before implementation, right? Like imagine how amazing it is that before any decision that you would take in life, you can see a foreshadowing of what's going to happen, and then you would decide maybe that's good for me, maybe that's not. Simulation is like that. It helps us reduce risks, costs, and failure. It allows us to run what if scenarios and analyze performance under a wide range of conditions. At its core, simulation is a numerical model. It's an equation. It's something mathematical that mimics the behavior of real life systems. It can be used during design, construction, operations, or even maintenance, right? All these options we can try with. For example, we might simulate a bridge's collapse under extreme loads or predict traffic delays during an evacuation. We can simulate different phases of a system's life cycle. In planning, we simulate needs and demand. In design, we model structural behavior. During construction, we simulate resource allocation. Like, where do I get my concrete? How much do I need? How much do I have? When do I need it? That's also important. And in operations or maintenance, we model deterioration or failure. Simulation is flexible. It applies from concept to end of life. Let's look at real-world examples of simulation. For example, simulating stress and collapse in structures. And that's what you do in Robot and Rivet and all these tools, right? Modeling traffic flow and emergency evacuations is another thing that you utilize. Predicting flood levels when we're designing dams, or simulating HVAC airflow in large buildings, which you learn in 414, I think, AE 414. Planning earth-moving operations, crane operations, dam releases, which we do in construction processes and construction equipment. Simulation helps answer questions we cannot afford to get wrong in reality. Simulation uses two types of numerical models: deterministic models, which are equation-based, same input, same output, and stochastic models, which include some sense of randomness. They reflect the real world more than the deterministic models. In civil engineering, we have to combine both. For example, we use the equation of randomness to predict the weather and the impact of the weather, but generally, the yield strength of steel is known, is in like 420 megapascals, give or take, based on impurities and so on and so forth. So generally, things like that are deterministic. The yield strength of steel should be within a specific range. If there is something that is usually affecting it to be in a different direction, then in that case, for example, the factory could be faulty, or something should be done to make sure that it's either corrected or never used again. So why bring in randomness? Because civil systems are not predictable. There is always something affecting it. So we can't always be sure that this is what's happening or this is what will happen. Materials have strength ranges, traffic fluctuates, costs escalate, weather changes, how that goes. It's never predictable. One day it's clear in the morning, the second you have a sandstorm. Random numbers let us simulate these uncertainties and estimate the likelihood of different outcomes. One of the most powerful tools in stochastic modeling is the Monte Carlo simulation. It runs hundreds or thousands of scenarios, each with randomly sampled inputs. This builds a distribution of outcomes instead of one single answer. We use it when equations are too complex or inputs are too uncertain, and we have a seriously wide variety. So instead of doing an infinite number of trials to figure out what is the most likely, we do a Monte Carlo simulation enough times for it to converge to the most probable outcome, like predicting costs or failure probabilities. So let's look at a simple example. Suppose we run 5 cost simulations and 2 of them exceed our $1.15 million budget. That suggests a 40% risk of running over budget. But 5 runs are not enough. So we repeat the simulation 100 times or even 1,000 and 10,000 times. The more we repeat it, the more sure and certain of the most probable outcome we become. The more we sample, the more reliable our estimation would become. So what did we learn? Simulation helps us engineers test ideas and manage uncertainty in a pseudo environment. It mimics real systems using deterministic or stochastic models, or usually both. Random inputs reflect how civil systems behave in the real world. They're always unpredictable. And one of the main tools we use is Monte Carlo simulation, where we create certain equations and designs, and then we iterate them many times until we get a convergence. And it's a key tool for risk-based design and decision-making for engineers. And that's the gist of simulation. Are there more tools and more approaches? Of course. But this is a good foundation for now before you get into more advanced courses about these topics. Best of luck.